So we just did a little demonstration of me pouring quote unquote beer into a Pilsner glass and looked at the different things that were changing. And there was a lot of things that were changing with respect to time. There was volume, there was height, there's radius, there's weight, etc. And all those fall under the heading of related rates. So this is section 3.9, related rates. Now, one of the things that you're going to have to be careful of in this section is that when you're working with these problems, it's always going to involve implicit differentiation at some point. So we'll start with kind of a friendly one to begin with. And that would be this one up here. So let me copy that down. That's going to be example A. If y equals 2x cubed plus 4x and dx dt equals 2, find dy dt when x equals 4. Find dy dt when x equals 4. So kind of a nice basic related rates problem. But this equation doesn't have any dx dt's or dy dt's in it. That should be a dy dt. So what am I gonna have to do? Well, I'm gonna have to differentiate this relationship, not with respect to x, but with respect to time. Now, with respect to x, this would be pretty easy, right? If I was doing dy by dx, what would dy by dx be? Anyone?
6x squared plus 4.
Yes, 6x squared plus 4. Thanks, Cole. But we're going to differentiate with respect to time, with respect to t. So we have y equals 2x cubed plus 4x. Now let me kind of do the same thing here that I did with implicit differentiation. I'm going to kind of pair those off or highlight these in some way to remind us that we got to use the chain rule or differentiate implicitly. So we're going to apply the derivative to both sides of this equation. In other words, d by dt. I'm going to differentiate with respect to time. That's what this means. It's the differential operator. So this first one is just the derivative of y with respect to t. Nothing big there, dy by dt. On the right-hand side, I'll ignore the 2. But what happens when I differentiate this? You've got to use the chain rule. It's going to be the derivative of the outside. So it'll be times 3. And then what happens when you differentiate here? The 3 comes down. What else happens? Somebody help me out here.
It becomes 3 minus 1, so 2.
Good, so there'll be a 2 there. There's still an x on the inside. So that's the derivative of the outside times the derivative of the inside. What's the derivative of the inside if you're differentiating with respect to t?
dx by dt.
Excellent, dx by dt. Thank you both. Plus, and then we'll have a 4 times, well, there's technically a 1 here, so 1 times 4 is still 4, except that'll be to the 0 power times the derivative of the inside. What's the derivative of that with respect to time? Someone help out Cole here. Go ahead.
Y. Oh, dx over dy or dt. dt.
Dx over dt. Perfect. Dx dt. So notice we had dx dt in a couple places, and that's okay. We can clean this up a little bit. We got dx dt in both of these places. So let's see about cleaning this up. That's going to be 6x squared plus 4. And then I'm just going to factor out the dx dt. So dx dt equals dy dt. Are we okay there? So this big first step was to differentiate implicitly. you have to do your related rates problems by differentiating implicitly. So we're good here. If not, I'm more than happy to work over some of this a little bit more. Now, they tell us a couple of these things here. We want to find dy by dt, so that's what we're looking for. Let's see, I think they gave us dx dt and I didn't write it down fully. Dx by dt was equal to 2, so let's put that into our equation. That's equal to 2 when x equals 4. So let's put in everything and then we can find dy by dt. So 6 times 2 squared, or excuse me, 6 times 4 squared plus 4 times dx by dt, which is 2. So 2 there and a 4 there. 16 times 6 is 96 plus 4 is 100 times 2 is 200 is your dy by dt. Nice. And that's it. So that's how y is changing with respect to time. All right, so kind of a friendly one to begin with. We're looking okay on that one. Something I can help out with. If not, we'll try another one pretty similar.
How did the dx by dt turn into a 2?
They gave us dx by dt was 2. That was part of the
Okay.
problem.
I saw x equals 4 and I thought, okay.
No, I appreciate you asking. Yeah, this was given right there. All right. Anything else on this one that looks a little perplexing? Maybe I went over a little too fast. Okay. Let's try another one similar to this one. A particle moves along the curve below. As it reaches the point 2, 4, the y-coordinate is increasing at a rate of 3 centimeters per second. How fast is the x-coordinate of the point changing? So let's see, there's a little bit more there at that instant. All right. So this one will become example B. Example B. By the way, did the PDF of this come through okay? In the chat?
Yes.
All right, thank you. So I'm just copying down some of the relevant information. So the things that I need to pick up here, of course, would be the function, but there's a couple other little things I want to take note of. We're looking at this at the point 2, 4, and the y-coordinate is increasing at a rate of 3 centimeters per second. How fast is the x-coordinate changing, x-coordinate of the point changing at that instant? So this long sentence that I have here underlined in yellow or highlighted in yellow, what does that translate to? Can anyone put that in math terms?
Not the slope.
It's not the slope, because that would be dy by dx, but it is a rate of change. So what rate of change would that be? Go ahead.
Is it the velocity?
It's not quite the velocity. But you guys are dancing around the right thing. So it's your dy by dt. It's how fast the point is changing with respect to time as this point moves along. So dy by dt was 3 centimeters per second. So I'll write that down. Maybe with that in mind, we can figure out the next one. Question is, how fast is the x-coordinate of the point changing at that instant? So what are they asking us to find? If I was to write down kind of a variable or something for this, what expression should I write down?
dx by dt.
Dx by dt. Awesome. So dx by dt is unknown. That's what we're trying to find. But we've got a lot of other things here. We've got X and we've got Y. So the first thing that we'll do is we need to come up with a relation between these. How are these rates related? And that's going to mean I'm going to need to differentiate this with respect to t. So I'll write this as y equals, I'm probably not going to leave it as 8 plus x cubed. What should I write there instead of 8 plus x cubed? Can anyone think of what I could do that would make my life easier to differentiate?
Put it to the 1/2.
Excellent. Put it to the 1/2 power. And then what we have to be careful of is differentiating this implicitly with respect to time. So have a nice big d by dt. This means, again, that we're going to differentiate with respect to time everywhere. Now on the left-hand side, it's just dy by dt. On the right-hand side, you got to use a chain rule. So somebody help me work through this. It's going to be the derivative of the outside. That's going to be 1/2 times 8 plus x cubed raised to what power?
-1/2.
Negative 1/2 times the derivative of the inside. Now the derivative of the inside is going to be, well, derivative of 8 is going to be 0. What happens when I differentiate x cubed?
3x squared.
Yeah, it's going to be 3x squared. And I did myself a disservice here. I lost those little brackets there. So it's going to be times 3x squared. But then I've got to differentiate the inside of this, right? Because I got to differentiate this implicitly. So it's going to be times 3x squared. What other term am I going to have here?
Times dx by dt.
Dx by dt. And that's our unknown. That's what we want to solve for. So, now let me clean this up a little bit. The 3x squared, that's going to be in the numerator. This I can put in the denominator. So it's going to be 3x squared over 2 times 8 plus x cubed to the 1/2 power. Notice that when it went from numerator to denominator that it changed signs. Dx by dt equals dy by dt. So I'm just cleaning it up a little bit. Now, I guess there's a couple ways we could solve this, but let's think about what we know. We know x, we know y, and we know dy by dt. So let's put in the things we know here. So the things that I know would include dy by dt is going to be 3. And then x is 2. So 3 times 2 squared. 8 plus 2 cubed to the 1/2 times dx by dt. So I'm just putting this in rather than actually finish solving for dx by dt. I'll solve for it after I get a number here. So that would be a 2 here and a 2 here. And let's see how this all works out. 3 times 2 squared is 12. That's going to be 2 times the square root of 16. So that's 2 times 4 dx by dt. So in other words, if I put this in lowest terms, I'll end up with 3 over 2 dx by dt. And last but not least, I can multiply both sides by the reciprocal, which would be 2/3. 2/3, 2/3. The 3's cancel out, and I get 2 equals dx by dt. Now you're fortunate in WebAssign in that they'll actually put in the units for you here. You know, they give you a little box and you put in your answer. The answer is 2, but the units are typed in for you. Now on a face-to-face exam, I wouldn't be doing that. You should know what units go here. Can anyone tell me what they think would be the right units for this?
Centimeters per second.
Centimeters per second. Excellent. So as y is changing at 3 centimeters per second, x is changing at 2 centimeters per second. In other words, y is changing faster than x at that point. Okay, how's that one look? All right, let's try a different one then. And I think let's see, yeah. I kind of smiled when I saw this one. They talk about the weight W of an astronaut in pounds is related to her height above the surface of the Earth in miles. So the Earth is about 3,960 miles in radius. Not quite a sphere. I think we're a little fatter around the equator than we are tall around the north and south poles. But if we kind of round it off a little bit, that's not a bad approximation. So the weight of this astronaut is given by this relation where W naught is her weight on Earth. So if the astronaut weighs 135 pounds on Earth and is in a rocket being propelled at a speed of 11 miles per second, find the rate at which her rate is changing in pounds per second when she's 45 miles above the Earth's surface. So, wow, a lot going on here. Let's see. Let's copy down a few things. This will be example C. W equals W naught, 3,960 over 3,960 plus H squared. Talking about the force of gravity. W naught is 135 pounds. The rocket's being propelled upward at a speed of 11 miles per second. So, that sounds like a rate. Aspen says hi. He thinks it's going too fast, but you have to be going at least, I think, 8 miles per second to reach orbit. So, wow. Yeah, that is fast. It's faster than the bunnies you chase in the backyard, isn't it? Yes. He doesn't catch them. They're even faster than him. So what could I write for this? What should I write? Is there anything in the equation that kind of looks... Well, let's see. Let's move on to something that we do know or can figure out. She is 45 miles above the Earth's surface. So that's H is 45 miles. But I still need to figure out that 11 miles per second stuff. What's that all about? What should I write there? Well, that's another rate. And it's the rate at which your height is changing. So what could I write? I don't know why he's so anxious about this problem. Maybe he's got fear of heights. I don't know. What could I write here for this 11 miles per second? And it should be really...
dt?
Yeah, thank you, Marley. dH by dt. So dH by dt is 11 miles per second. We want to find how her weight is changing under these circumstances. So dw by dt equals all this. All right. Okay, so we need to find dw dt. That means we need to differentiate this with respect to time. Now, I think before I do that, I'm going to plug in the W naught as 135. 135, 3960 over 3960 plus h squared. Now we got to differentiate that with respect to time. So d by dt. On the left-hand side, we get dw dt, which is what we want to figure out. On the right-hand side, it's going to be a constant. And let me rewrite this right-hand side a little bit, just to make it a little bit easier for ourselves. Because I don't know about you, I don't really want to use a quotient rule. Anyone out there want to use a quotient rule? Well, we can avoid, yeah, we can avoid it. So let me help us avoid the quotient rule. I'm going to write that as 135 times 3,960 squared from the numerator, and then 3,960 plus h squared in the denominator. Now, why does that help me? Well, I can further rewrite this as, let's see, 135 times 3960 squared times 3960 plus h to the negative 2. Now I don't have to use a quotient rule. All I got to use is the chain rule, and I'm much better off. This is something I tried to convey to you last time when we were working with something that had some quotient in it. I'm like, look, if you can avoid the quotient rule, sometimes it's not a bad idea. It's not a universal thing. Sometimes it is just convenient to use a quotient rule. Well, let's see if we can't differentiate this. So let me kind of move this down here. dw by dt. If I differentiate this and this, well, these are constants, right? I can ignore those. So let me just write 135, 3960. And now I can focus on differentiating this. Well, let me just do one thing here to try and be consistent with examples A and B. I'm going to put a little bracket around that. Why am I taking the time to put a bracket around that? Can anyone suggest a reason?
If you use chain rule on it, also you lost the square.
Yep. Where?
Right there.
Yeah, thanks. All right, so that's going to be my h here. When I differentiate this, you got to start with the derivative of the outside. So the derivative of the outside means a negative 2 is going to come out in front. And then what happens? Then you subtract 1, so you get negative 3 times the derivative of the inside. And when I differentiate the inside, well, at least it's pretty straightforward. Derivative of constant is 0. Derivative of this with respect to t is going to be my dh by dt. dh by dt. Okay. I think that does it. Yay. So all of this is in the numerator. This is in the denominator. We get negative 2 times 135 times 3960 squared divided by 3960 plus h cubed dh by dt. And now it's time to plug in some of the things we know. For instance, we know what the height is. The height was 45 miles. We know what the change in height, you're traveling at 11 miles per second. So 2 times 135. Can anyone suggest a reason why this is negative. What's that telling me about this whole problem?
As height increases, she loses weight.
Yeah, her weight is decreasing as you increase the height. That's what the negative sign reflects there. Good job. 45 and 11. And yeah, I think that's it. It's just a matter of calculation now. So let's do that. I don't have that started. I'm just going to go over to here then. So if you hit the, come on. If you hit this alpha key and then the y equals key, they give you a nice fraction. So you can type things in with the numerator and denominator. Now, I guess since this is up and running now, I'll just do it here. Clear. Again, alpha key, then the y equals key. Might make it a little bit easier. I'll type in the negative 2 times 135 times 3960. All that goes in the numerator. Yeah, that should be squared still, right? Yeah, squared divided by parentheses. Actually, I don't really need the parentheses. If you can do the add in your head, it'd be 4,005. And that would be squared as well. Something doesn't look right.
Parentheses up top.
No, I don't think I need parentheses. Let's see, I forgot to multiply this by 11. Still doesn't sound right. Was it times 11?
The denominator is cubed.
Oh, it's cubed. Whew. Thanks. Thank you. So let me do this one again. If you hit the second key and the enter key, it'll bring up your previous calculation, which is kind of cool because then you can just edit it. So I need a times 11 here. And in the denominator, see if I can go down to the denominator. There we go. I need to make that a 3. Whew, there we go. That makes much more sense. Her weight couldn't be decreasing at 263 pounds a second, right? That just wouldn't have made sense. I mean, you know, in less than a second, all her weight would disappear. That didn't make sense. So thank you so much, gentlemen. Yeah, negative 0.725, you know, about 3/4 of a pound every second, her weight is decreasing. So about negative 0.725 pounds per second. Yay. Comments or thoughts on that? These are challenging problems, and you know, I'm not going to lie to you about that. We're going to try and do as many practice problems as we can, but don't worry. I put no more than 15 or 20 of these on any exam, so you should be okay. All right. You can't see that I'm smiling too well, but it's just a joke. I don't overload you with these kinds of problems, but there will be a couple. So those of you who are striving for that A, make sure you can do these.
This isn't the only section we're covering today, is it?
No. It'd be nice. I wish we had that kind of time, but we don't. Let's move down to this one down here. This one looks kind of fun. A snowball. If a snowball melts so that its surface area decreases at a rate of 3 centimeters per second, let's write something down right now. What can I write down for that? What can I write down for the surface area? Well,
dA over dt.
yeah, dA over dt. I'm gonna write ds over dt, but same thing. So example D, we'll do ds by dt equals 3 centimeters per second squared, or 3 centimeters squared per, actually per minute. All right, find the rate at which the diameter decreases when the diameter is 11 centimeters. So the diameter, D equals 11 centimeters. Let's see, I'm trying to think how big that'd be. That's a pretty big snowball. 11 centimeters? No, okay, 11 centimeters. That's about what, 4 inches? That's about right. That's about right. Still wouldn't want to get hit with it if, somebody's throwing it pretty fast. So the hint that I gave you is not quite accurate. And there's actually a little change that I would make to it. Reminds me of something that I like to tell people, or I like to show people. And that is this. Let's start out with the area of a circle. This is just a brief aside here. Maybe I should do it on a separate sheet of paper here. So what's the formula for the area of a circle? Does anyone remember? Pi r squared. If I were to differentiate this with respect to r, so apply dr by d by dr, the right-hand side would be dr, or dA by dr. Excuse me, the left-hand side would be dA by dr. The right-hand side is what? Well, you can just differentiate this in the regular way because you're differentiating with respect to that variable. You don't have to do any implicit differentiation. What's the derivative of pi r squared? Well, pi is a
2r.
constant. 2 pi r. Does anyone recognize this formula? This is for the area of a circle. What's this formula?
Circumference.
It's the circumference. Circumference. So when you're changing the radius of a circle, that change is felt right at the edge, is felt at the circumference. That's what's changing. Let's bump this analogy up one dimension. So when you differentiate the area, you get the circumference. How about if I add a volume? Volume of a sphere is 4/3 pi r cubed. If I did dV by dt, if I differentiated that, then what would I get? Can anyone actually, let's differentiate with respect to r. What would I get there?
3 pi r squared.
Good. Now the threes cancel, so we're left with 4 pi r squared. But what this is the formula for the surface area. And it's just a derivative of this. So, yay. I never really actually remember this formula. Just outright, I always differentiate this one to get this. So, in any case, that's the formula that we need here. I accidentally wrote down another one because I didn't look at the problem carefully enough. So S equals 4 pi r squared. We'll kind of keep that around. And they tell us something about the diameter, right? The rate at which the diameter decreases when the diameter is 11 centimeters per second. So what we're looking for is, I hate using this, dd by dt, right? If you want to come up with some different variables, I'll use a capital D for diameter. dd by dt equals that. One little problem that we're going to run into is that this is in terms of the radius. So how do the radius and the diameter relate to each other?
Diameter is twice radius.
Diameter is twice the radius. So when we're all done, we're gonna have to divide our result by 2 because dd by dt is gonna be 2 times dr by dt. Or actually, we have to multiply our result by 2, depending on what we get. So just something to keep in mind for when we're all done with this problem. But for now, let's come back up here. This relationship, I spent a minute or two trying to come up with that relationship. Let's see if we can't differentiate and get it, or get a relationship that we need here. If I'm going to be consistent with what I've done with all these problems, I've got to remind ourselves that we've got to differentiate implicitly. So why don't you see if you can't differentiate that one implicitly? So on the left-hand side, you're just going to get ds by dt. On the right-hand side, this is a constant, this is a constant, that whole thing's a constant. So basically you're going to have to differentiate r squared. So the thing you got to keep in mind is we're differentiating not with respect to r, which would be easy, we're differentiating with respect to t, which means this term gets differentiated implicitly. Derivative of the outside is going to give me a 2, multiplying this gives me 8 pi times r to the first power times the derivative of the inside, which is dr by dt. So that's your derivative there. I'll pause here, comments or questions there, something that doesn't look quite right, etc. There is something that I noticed that we need here that I don't have just yet. The things that we can fill in, let's fill those in. That's a 3 here, 8 pi. I don't have r. And I'm looking for dr by dt, so I don't have that either. What am I going to do for these? It's actually one of these I can fill in. Can anyone tell me which one I can fill in?
R would be half the diameter.
Excellent. So it's not really given to us, but it's kind of implied here that radius is 11/2 centimeters, half of that. So let me put that in here, 11/2. And then dr by dt, well, that's our unknown. That's what we're trying to find out. And once we find that, we'll double it to get dd by dt. The 2 cancels out. That gives me 3 equals 4 pi times 11 dr by dt. And I don't know why I didn't just do that in my head in the first place. So 3 equals 44 pi times dr by dt. Dividing both sides by 44 pi, I get 3/44 pi equals dr by dt. I'm almost done. According to this relationship here, I need to double that to get dd by dt. So 3/44 pi times 2 is going to be 3/22 pi, because 2 of those will cancel, and that's going to be dd by dt. Wow, good stuff. Good stuff. Oh, I should put some units here, right? Can anyone tell me what units would be the correct units here? You got to be careful on this one.
Centimeter per minute.
Excellent, excellent. It's going to be centimeters per minute. Now up here, we were initially given centimeters squared per minute. That's because this is an area, so you're dealing with square units. Down here, the diameter is just a linear measurement. There's only one dimension, so it's going to be centimeters to the first power, or just centimeters per minute. Excellent, well done. unless they ask you for a decimal approximation, give them an exact answer in WebAssign. My advice. All right. Comments or thoughts on example D here? Okay.
No.
No. All right. Let's keep going. This one's very typical of a lot of related rates problems. So let's knock this one out. A plane flying horizontally at an altitude of 1 mile and a speed of 420 miles per hour passes directly over a radar station. Find the rate at which the distance from the plane to the station is increasing when it's 4 miles away from the station. Round your answer to the nearest whole number. Wow, a lot going on here. Let's see if we can't make sense of it. So this will be example E. Let me just try and draw a sketch of what's going on here. Okay, so here's your radar station. And you got a plane that's passing overhead. And it's passing at a height of y equals 1 mile. And it's traveling at 420 miles per hour in the horizontal direction. We want to know how fast it's moving away from us when it's 4 miles away. Now, the thing that I'm not sure of is that at 4 miles horizontally, or is that 4 miles from the actual radar? I'm going to go with 4 miles this way. I'll call this Z, and I'm going to call this X. So what does it look like I'm setting up here? Can anyone think of a relationship that might bring together X, Y, and Z?
Pythagorean theorem.
The Pythagorean theorem, yeah. Pythagoras actually had a little bit of a humorous side to him. He invented a prank cup, and it was for greedy guests at parties. So if you filled up your cup with wine, a modest amount, it was fine. But if you filled it up too much, it created a vacuum and drained all your glass onto your hand or clothes or whatever. It's kind of funny. Look it up, Pythagoras prank cup. But what we remember him for now is this one. X squared plus y squared equals z squared, the Pythagorean theorem. And this is what we need here. Now, they tell us a few things that are helpful. They tell us what X is. X is, well, actually, they don't tell us what X is. They tell us what Y is. Y is 1 mile. Z is 4 miles. And let's see, what we don't know in all this is what we want to find out, which is dz by dt. How fast is that distance changing? We don't necessarily know what dy by dt is, but we do know what dx by dt is. What's dx by dt going to be in this one? Can anyone tell me?
420 miles per hour.
Yep, 420 mph. Awesome. We actually do know what one of these other ones is, but let me take this relationship and do what we have to do in all of our problems, and that is differentiate with respect to time. Now,
How do we know that dx dt is 420 miles per hour?
Oh, great question. Let me go back to the problem. It says A plane is flying horizontally at an altitude of 1 mile at a speed of 420 miles per hour. So that's how fast it's changing its position horizontally.
Okay, thank you.
Yeah, no problem. So I'm going to differentiate this implicitly with respect to time. All of these things get differentiated with respect to t. So this is applying our differential operator, d by dt times this. And let's see here. It's going to be the derivative of the outside times the derivative of the inside. The derivative of the outside is going to be 2x to the first power. I'm not going to write to the first power. Times the derivative of the inside. So can someone help me out here? Talea, what's the derivative of the inside going to be?
Let's see.
So I've got the derivative of the outside, which is my 2x to the first power. What's the derivative of the inside?
Would it be d over times d over dt?
dx over dt, yes.
Oh, yeah, dx over dt.
Good. Can you try this one as well? What's going to happen here?
So it's going to be 2y
Mm-hmm.
times.
Outside.
So would it also be times dx over dt?
No, wouldn't be dx over dt.
dy.
dy over dt. Cool. And since you're on a roll here, want to do the last one?
Sure. So 2z and dz over dt.
Yay. Yeah, dz over dt. Nice. Thank you. If you look here, there's 6 unknowns, but we actually do know a couple of them, and we can get some other ones. So one thing I guess I would do here is I would divide this whole equation by 2. Why? Well, because I can cancel out the 2 from each of these terms. It just makes it a little easier. You don't have to do it, but why not? If you look at what we've got, we're missing a little bit too much. You can only have one unknown, but right now I see x is unknown, dy by dt is unknown, and dz by dt is unknown. Now this is the one that we're looking to find. But this one, we actually don't know, but we can figure it out. Can anyone tell me how I can figure out x? Let me help you out here. Pythagorean Theorem. Bam, just plug it in. So it's going to be x squared plus 1 squared equals 4 squared. So x is going to be the square root of 15. All right, so we got that one. Square root of 15 miles. So a little bit under 4. I still need to know this, dy by dt. But we can think about that one. dy by dt, that's how the height of the plane is changing. How much is the height of the plane changing if it's flying horizontally?
None. 0.
None. None, aka 0. Yeah, 0. And if you look at these things now, we've got 5 out of the 6 of them. That means I can substitute and solve for the remaining one. But the height is not changing. How do we know that? It says the plane is flying horizontally. Where'd it go? Rats. There we go. Horizontally at an altitude of 1 mile. So cool. All right. Let's substitute in and solve. That's going to be square root of 15 times dx by dt, which is 420, plus y, which is 1 times 0, equals z, which is 4 times dz by dt. This term cancels out. So I get 420 times the square root of 15. If I divide both sides by 4, I'll end up with 105 times the square root of 15 equals dz by dt. And you can come up with an approximation. In fact, I think they ask you to have an approximation. So 105 times the square root of 15. I think they wanted you to round it to the nearest whole number. So it'd be about 407 miles per hour. 407 mph dz by dt. So basically, most of the change in that, the distance is reflective of its horizontal change in position.
Wait, why is dy over dt 0 again?
Because dy by dt, its height isn't changing. Its height is always 1 mile. So there's no change in the height. So dy by dt would reflect the change in the height at any particular time. But if you're flying level, you're not going up or down, your y height isn't changing. Is that addressing your concern?
Yeah, thank you.
Okay, cool. Thank you.
Could you move the paper down just a little bit for a second?
Yeah.
Thank you.
Mm-hmm. Any other comments or thoughts on that one? So we're going to do another example of a Pythagorean theorem type problem. This time we've got a ladder leaning against a barn when its base starts to slide away. Now, if you've got this link open, then you can take t and start increasing it. And ooh, ah.
Wow, look at that ladder go. What are you, an animator now? Man, I signed
Man.
up for a math class and I got this. That's crazy.
This is awesome. This is so cool. Now, the thing is, the height of the ladder, you know, as a function of time, changes in kind of a weird way. If you notice, towards the end, the bottom just kind of drops out. It just, boy, it falls. But near the beginning, as you're moving things out, you know, there's not much of a change in y given the change in x. So you move things out a little bit, it doesn't create a big change in height. But by the end, bam, it just really, really falls. So let's see if we can't do this one. So we've got a 17-foot ladder is leaning against a barn when its base starts to slide away at a constant rate of 1 feet per second. Let's do ourselves a favor like the last one and draw ourselves a picture. So this would be example F. All right. So here and here. So I like labeling them in X, Y, and Z fashion because these reflect the usual directions that we have. And we know that Z, for instance, is 17 feet. Okay. What else do I know here that I can put down? So let's see. From my experience with the last one, I know I'm going to need an X, Y, and Z. And I also know that I'm going to need dx by dt, a dy by dt, and a dz by dt. So I'm just going to kind of get that out of the way right away. Let's see what variables I can fill in. A 17-foot ladder is leaning against the barn when its base starts to slide away at a constant rate of 1 feet per second. So 17-foot ladder, what's that 17 going to be? what variable that I have on my list.
H.
I don't have an H as part of my list. So on my list, I've got X, Y, and Z, dx, dy, and dz by dt. So which one of these is that 17?
C. Y.
Well, y would be the vertical height, right? So z has to be the hypotenuse. So z would be 17 feet. Are you okay with that? That seems like a little.
Yes.
Okay. All right. Just checking here. When it starts to slide away at a constant rate of 1 foot per second. 1 foot per second. So that's a rate. So of my choices here, it has to be one of these three. I've narrowed it down that much.
dx by dt.
Cole thinks it's dx by dt. Do you agree, or do you think it's something else? What do you think? Dx, dy, dz by dt. Which one of those? Or is Cole right? Well, Cole is right. It's 1 foot per second. So I'll put that there. Let's see what else we can pick up. How fast is the top of the ladder sliding down the barn wall when the base of the ladder is 8 feet from the barn wall along the ground? So they've told us something else here. We're looking at figuring out how far or how fast the ladder is sliding down the wall when the base is 8 feet from the wall. So what's this 8 telling us? What information
X
can I
is
fill
8.
in? X is going to be 8. And that's nice because it's a Pythagorean triple. So X is going to be 8. You can figure out Y from 8 squared plus Y squared equals 17 squared. So that's 64 plus Y squared equals 289. Y squared equals 225. Y equals 15. Technically, there's a plus and minus there, but we're not going to think about a negative length here. So 15 feet. We got that from our good old friend, the Pythagorean Theorem. Which one of these variables are we looking for? We got 4 down. One of these has to be our unknown. Is it dy by dt or dz by dt? How fast is the top of the ladder sliding down the barn wall when the base of the ladder is 8 feet from the barn wall along the ground?
It's dy by dt, and then dz by dt would be 0.
Somebody explain to me why dz by dt would be 0. Don't make Cole do all the work. Why
The
is
length
dz by
doesn't
dt?
change. It's always
Yeah, it's always 17 feet, right? So the
Yeah.
length doesn't change. So, okay, that's fine. And dy by dt is how high the tip of the ladder is. And as that comes down to wall, that's going to be your dy by dt, the rate at which the height is changing. So that's our unknown. Can we skip the implicit differentiation step from last time and just jump to kind of the happy ending on this? It's going to be dy or x dx by dt plus y dy by dt equals z dz by dt. And let's just fill in all that we know and all that we don't know. So x is 8 times 1 plus y, which is 15 times dy by dt equals 17 times 0. In other words, 8 plus 15 dy by dt equals 0. Dy by dt, move the 8 over, divide by 15, negative 8 over 15. And that would be in feet per second. All right. Let's think here. Before I ask you questions about this, let me ask you, are you okay with this calculation?
Yeah.
Okay. All right. Let me ask you a question. Michelle, why is that negative? Why did what I got here, why is it negative? Can you interpret that in terms of the problem? Why dy by dt is negative? And maybe we'll look back here at the graph and change this. What's happening that makes dy by dt negative? So here it is at time 2, down to, bam, time 17. Michelle, you out there? No, Michelle. All right. Tyler.
Sorry about that. The realistic.
So what's going on that the sign of my answer is negative? What does that reflect? Because the last one wasn't negative. The last one was positive.
Slope decreasing.
Not exactly the slope, but the height is decreasing. So yeah, pretty much what you said. So the height is decreasing because as time goes on, the height is getting smaller. So you're decreasing. So we expected a negative value for y here, or a negative value for dy by dt, makes sense. Whereas in the last one, things were positive because the plane is moving farther away. So that distance is going to increase over time, not decrease. So that's why it was positive here and negative here. You want to pay attention to those things because, you know, a small slip of the sign could mean the difference between getting it right and wrong. Okay. Any other thoughts on this one? Let's do a couple more, and then I think we'll call it a day on this. Actually, maybe just this last one right here. A cylindrical tank with a radius of 3 meters is being filled at a rate of 4 meters cubed per minute. How fast is the height of the water increasing in meters per minute? So, wow. All right, gonna have to do a little bit of thinking on this one. So we've got a cylindrical tank. So got our cylindrical tank here. And it's 3 meters in radius, is that right? Yeah, radius is 3 meters. That's a lot of liquid in that tank. Better be holding quite the party. 3 meters. And we want to know how the height is changing with respect to time. How fast is the height of the water increasing in meters per minute? So, wow. We're going to have to think a little bit about this one. And let me help you remember the formula for the volume of a tank like this. So let's just start with the base. What shape, despite my poor rendering here, what shape is the base in? If it's a cylindrical tank?
A circle.
A circle. Thank you, Tyler. So that's going to be a circle. And the area of a circle is pi r squared. But I want the volume. And to get the volume, all I need to do is account for the other dimension in this problem, which is the height, h. So the volume is going to be h times pi r squared. That's the volume of a tank. Now, what do they tell us? They told us that the radius is 3. And what else did they give us? They give us that water is being filled at a rate of 4 cubic meters per minute. So what's that? What are they giving us there? What can I put here? 4 cubic meters per minute, but what is that?
dy over dt.
dy over dt, yeah, I see where you're getting that. But related to this problem though, because I know that volume equals h times pi r squared, or I always think of it as pi r squared times h. What is it in this particular problem? Anything?
Is it volume per minute?
Yeah, volume per minute, or dV by dt. That's how fast your volume is changing. And they're asking us for, let's see, where was it? How fast is the height of the water changing? So that's going to be dh by dt is unknown. And I guess there's one other quantity that's kind of in here, and that is dr by dt. But dr by dt is 0 because the radius isn't changing. It's a cylinder. It's not like a nice Pilsner glass where it's tapered and the radius changes. It's just straight. In fact, if we want to, we can just plug in this 3 right away and get that our volume is 3 squared, which is 9 times pi times h. So that's our volume. If you couldn't do that, if this was some variable number, then you'd have to differentiate this using the product rule and implicitly. So we're kind of nice there. Volume equals 9 times pi times h. Let's differentiate that implicitly. V equals 9 pi times h. Let's put little brackets around this one. That's going to require a little extra special care. And I'll give you a minute to take a shot at that. Try and tell me what we get when we differentiate this implicitly. Put it in the chat. Okay, so the left-hand side is going to be dV by dt. If you apply this to the right-hand side, 9 pi is a constant, so you can ignore that. Derivative of this, pretty much similar to the derivative on the left-hand side, it's just going to be dH by dt. If we fill in what we know that the volume is 4 equals 9 pi times dH by dt. That's our unknown. That's what we want to find. So divide both sides by 9 pi and get dH by dt. What units would go with that? They actually say it in the problem. It's meters per minute. Keep in mind that this is a height which has 1 dimension. So it's going to be meters to the first power. It's not going to be meters cubed. The original thing that they gave us was in cubic units because this was a volume. Volumes in cubic units, areas in square units. Linear units are just to the first power. All right. How are we looking on that one? So I think maybe we'll call it a day on this one here. Certainly one of the more common examples, and we did 2 of those, was the Pythagorean Theorem type examples. But these types of problems can be written in all kinds of ways. In fact, if you just look anywhere, I mean, you could see related rates happening. So good luck with this stuff. And expect one on the exam, 1 or 2 on the exam next week.